Welcome to the last lesson in Calculus AB. So this is to find the volume of a solid. It's another method, and this is called the shell method. And to begin, we're going to look at a rectangle here as our representative rectangle. Let me see if I can fix this then. So we're going to see, this would be the shape that we would get if you took that rectangle that I've highlighted and you've rotated it about the x-axis. So it's just a thin little rectangle rotated all the way around. So it would be like a, I don't know if you've ever seen a foam roller. They've got this outside, like, edge of a cylinder, and then the inside is open. It's sort of like this shape. So it's just an empty cylinder with just an outer edge, but the inside is hollow all the way through. It might help if you looked at page 457. So it would just be a shell. The inside is empty. And so we would have W to be the width of the rectangle. And then the height of the rectangle would be this. Remember, if we set the cylinder on its basis, then that would be our height. And let's see, the P is the distance between the axis of revolution and the center of the rectangle. So just taking the center of the rectangle to the axis of revolution, that is P. And that's important that it's the center of the rectangle. So when you take that rectangle and you revolve it around the axis of revolution, it makes a cylindrical shell or a tube of thickness W. To find the volume of this shell, we're going to think about two different cylinders. We're going to think about the actual cylinder that's there, formed by rotating that rectangle, and then the cylinder that is all that empty space. So the radius of the larger cylinder is the radius of the outer shell. So we'll call that the outer radius. And that is P plus W over 2. So it's P plus half of W. Remember, P just went to the center of the rectangle all the way to the axis of revolution. So to get the full radius from this outside part, then we would have to take half of that W and add it to the P to get that full radius. All right, and then the inner radius, which would be the empty part, the inner cylinder, that is P minus W over 2. Okay. P would be the average radius of the shell. So if we were to add these two radii together, you don't have to do this. And divide it by 2. Add them up and divide by 2 because there's 2 of them. You'd get 2P, and the W over 2's would cancel, and 2P over P would be P. So that's why they say P is the average radius. Of the shell. Okay. Now, so if you are not into the theory of this, you can fast forward until I get to the formula and work an example. It's completely up to you. So the volume of the shell is the volume of the cylinder minus the volume of the hole. So volume of a cylinder is pi r squared h minus pi r squared h, because these are both cylinders. So it's pi, the r, remember the outer radius we wrote was p plus w over 2 squared h, minus v, whoops, I wrote v. I meant for that to be pi. Pi, the inner radius is p minus w over 2 squared h. So when you FOIL and combine like terms, I'll just run through that. I'm going to pause it and show you what I get. Okay, so I FOILed this out and I got this. And when I combine like terms or distributed my negative, I got this. And when I combine like terms, I got this. And the book changes it to write it in the form of 2 pi PHW, just so I can be consistent. So it's 2 pi. P is our average radius. H is the height. And W is the thickness or the width. Okay, so that's our formula for the volume of a shell. And then I work with it a little more. Oops. I don't know what I did there. There. Okay. And let's see. Then we would call it 2 pi P of y, h of y, dy for our width, because it is a y value for w right here. Whoops. And then you can approximate the volume of each of those. This is our representative rectangle, but we could approximate the volume of the solid by saying it's the sum from I equals 1 to n, just like we were doing in class, of 2 pi times p of y, h of y, h of y, delta y. And then they said, just like in class, as the norm approaches 0, as the largest subinterval for dy gets smaller and smaller and smaller, so that happens as n gets larger and larger and larger, then this would be the limit as the norm approaches 0 of this formula, 2 pi sum I equals 1 to n, p of y, h of y, dy. And that, my friends, is the integral is equal to 2 pi times the integral from a to b of p of y, h of y, dy. So that's why we did all this, so we could find this formula. And that's the formula we're going to use for the shell method. So, example 1. Find the volume of the solid of revolution formed by revolving the region bounded by y equals x minus x to the third and the x-axis between 0 and 1 included, about the y-axis. Okay, so we have a vertical axis of revolution. If you look at the top of page 458, we have a vertical axis of revolution, so we're doing a similar version. The volume is 2 pi integral from a to b of p of x, h of x, dx. All right, so, and you can see the picture of why they're doing that. The representative rectangle is perpendicular to the x, so it's a dx. That's different than the Wescher method. So, we have a graph on page 458. I'm not going to try to graph it because I need all my room. So, it's 2 pi. A and B are x values, so it's from 0 to 1. P of x is the outer radius. No, it's the average radius. So the average radius is x. And if you look in the book, it explains, there's a picture. Let me just show you the picture. I can't get it to take a picture for me. Remember, P went from the center of our representative rectangle to the axis of rotation, and we don't know that value, so we just call it x. So it's some x value. And then h of x is the radius, so it's our function, x minus x to the third dx. The reason the height is the function is because the height of this rectangle, no matter where it is where the rectangle hits the curve. That's what establishes the height. So no matter where you draw the rectangle, its height is represented by a function. So we put the function there. And we're just ready to integrate now. The hard part was getting it set up. So it's 2 pi integral from 0 to 1 x squared minus x to the 4th dx. That's 2 pi x to the 3rd over 3 minus x to the 5th over 5 from 0 to 1. So that is 2 pi times 1/3 minus 1/5 minus 0. So that's 2 pi. 5 minus 3 is 2/15. So that is 4 pi over 15. Okay, I'm going to do one last one. Example 2, find the volume of a solid of revolution formed by revolving the region bounded by the graph of x equals e to the negative y squared, the y-axis, between 0 and 1, about the x-axis. So since we're rotating about the x-axis, that's why everything's in terms of y. So when you look at the graph, there's a nice picture for us on page 459. Here's our nice picture. This is the picture of the graph. If we didn't have a picture provided, we would just have to use our calculator to sketch it. And they want us to use the curve they gave us. They want us to use the y-axis and y between 0 and 1. So that's y equals 0, and here's y equals to 1. So there's our sketch, and then we're going to rotate it around the x-axis, it said. So you would have, you would have this shape. And rotated around the x-axis, you would have all this volume that we would find for this figure. All right, so now that we know how it's set up, and we know it's about the x-axis, that's horizontal axis of revolution. So on page 458, we're going to use that first formula. P is 2 pi from C to D of P of y, H of y, dy. And nice that everything's set up in terms of y. So it's 2 pi. When you look at your graph, the y values are 0 to 1. Or you can look at your limit here. 0 to 1. P of y is it's just a random y value. And because that's our radius, and our height is the function, because it varies depending on where the rectangle hits the function, dy. And when we integrate that, we're going to use a u substitution. If u is our exponent, then du is negative 2y dy. We have y dy already. We'll do a negative 2 and a negative 1/2. So we get negative pi on the outside. Oh, and we need to change our limits of integration. If y is 0, then u is 0. If y is 1, then u is negative 1. So from 0 to negative 1 of e to the u du. So that is negative pi of e to the u, evaluated from 0 to negative 1. So that is negative pi e to the negative 1 minus e to the 0. That's negative pi. 1 over e minus 1. That's negative pi. 1 minus e over e. And that's how we can leave it. And if you plug that in, because those are all numbers, you could have integrated this. You could have plugged in values much sooner. You could have stuck it in the calculator right there. But when you plug it into your calculator, you get 1.986. So shell method, it is possible to do this method on all these problems that I just showed you shell method for. So that is why I don't feel too badly that you didn't have class time for it. But example 3 is interesting because it's the one, I believe, exactly that I posted the video on for you. Let me just make sure I post 1, 0. Yeah, it's the exact same one as the example 4 from 7.2. They're just showing you how to use the shell method with it instead, and that the shell method might be easier. But they run through, actually, it's very nice. Example 3 on page 460. They show you how to do it with the way that we did it on my video, and then how to do it with the shell method. And both ways give you the same answer, but you don't have to separate two different integrals. So that wraps it up. You can try a couple of these. In fact, I would just try just a few on page 462. I'll see you Wednesday.